Hey, today we're going to talk about 1.4, carbon cycle. So take a moment, review the enduring understanding, check out the learning objective, and pause the video, review the essential knowledge, and set up your Cornell notes. So the carbon cycle is one of our first biogeochemical cycles. What? Where's this word? What does it mean? Well, let's break it down. Bio, living organisms. Geo deals with earth or rocks. And chemical deals with different molecules. So these are different molecules being transferred or cycled between living organisms and abiotic portions of the planet. So the first one is the carbon cycle. Carbon cycle you should have done in living environment and discussed it, but I am going to break it down further for you. So we have carbon reservoirs and carbon sinks. Just based on the definition of the word, a reservoir is something that is held temporarily, and a sink, not like a kitchen sink, although it could be kind of like a kitchen sink, but a sink meaning it's locked away forever. Not forever, but for a very, very, very long time. Geologically speaking, could be millions or even billions of years. All right, so typically, we think about the carbon cycle in terms of carbon reservoir and carbon sink. A lot of the other biogeochemical cycles have reservoirs and sinks, but typically for carbon, you will have to specify which one. And I have them color-coded here, and you will be doing a hands-on activity in class related to the carbon cycle. So first thing we have, I'm going to go over some processes. We have photosynthesis and respiration. And photosynthesis is when you are making glucose from carbon dioxide. So it's taking it from the atmosphere, the CO2, and converting it to glucose. Respiration is taking that glucose and respiring or giving off the carbon dioxide. Both of these are reservoirs. Another one, decomposition. So when something dies, it is decomposed. It's the glucose is converted into, broken down into other nutrients, and a lot of times this decomposition will also release carbon dioxide in the process. Gas exchange is gases being exchanged between plants and the atmosphere, between humans and the atmosphere, between the ocean and the atmosphere. All of these arrows going back and forth are gas exchange. Sedimentation and burial are kind of similar. Sedimentation is when things fall down from either from the atmosphere down to the soil, or sedimentation is falling, carbon-based substances falling down to the bottom of the ocean, like seashells from dead organisms or dead exoskeletons. And then when they are covered by other substances, that is considered burial. And over time, that can cause something to fossilize, and that is where it is basically like really, really condensed, very high carbon chemicals, and very rich in carbon. And we'll be talking about fossil fuels later on. Fossilization can occur on land. It can also occur in the ocean. You can get limestone. And then what happens is through tectonic activity, through the movement of the Earth's crust, you will have uplift, where rocks that were buried deep beneath the surface are now coming up towards the surface or beyond the surface and forming new mountains or other structures. And then once you get this new uplift, you get these new mountains, you'll have weathering, which is when the different parts of the rocks are breaking down, so those carbon-based substances can then move. And then this is where humans come in. We have extracted. So we've extracted these fossil fuels, or these fossilized remains, and we have made fuels out of them where we combust or burn them, releasing carbon dioxide back into the atmosphere. Anytime you burn carbon, you will get carbon dioxide as a byproduct. End of story. Okay? So anytime you have combustion, please, please, please remember it is combustion of organic material because it has to have carbon present. So it has to be something organic requiring carbon that is then being released into the atmosphere. Anything that has carbon and hydrogen in it is organic. So in this example, H2CO3, organic. Glucose, organic. Methane, CH4, organic. CO2, inorganic. Calcium carbonate, inorganic. Keep that in mind. Now, we have noticed over the past 50, 70 years that we have been increasing the levels of atmospheric carbon dioxide. And this has been going on for well over 100 years. Scientists have suspected this, and it's become a major event in the news, especially over the last few years with the crazy weather patterns we've had. So in the past, they have monitored the atmospheric carbon dioxide at Mauna Loa, which is an island or an observatory in Hawaii, and it's pretty far away, it's pretty secluded, so you can get a really good representation of just what the atmospheric carbon dioxide levels are, as opposed to being like downwind from a city or a metropolitan area, which you could have some carbon dioxide that could be, adjusted or altered because of the actions of humans. So this is pretty secluded, and it's a good place to measure it. So you notice that it has gone up, and it's kind of... So what happens is you have more carbon dioxide in the atmosphere in the winter because the plants aren't taking it in, and a lot of the leaves that might have fallen may be decomposing, releasing carbon dioxide back into the atmosphere. Now in the summer, the leaves are re-emerging, and they are pulling the carbon dioxide out of the atmosphere. So it rises in the winter and settles in the summer. Now this, you would think, we have a northern hemisphere and a southern hemisphere. When it's winter here, it's summer down here, and vice versa. If you look at a globe, most of the land, most of the terrestrial biomes are found in the northern hemisphere. Most of the southern hemisphere, comparatively speaking, are water, are aquatic. So typically the northern hemisphere, those the boreal forest, the northern forests in Russia, in Canada, Scandinavia, the taiga, that is driving the global carbon dioxide levels. So in the summer, CO2 is down, in the winter it is up. Now, what is the percent change in carbon dioxide between 1990 and 2000? So how do we solve this? Well, first of all, we want to identify. At 1990, we had about 355 parts per million, ppm, parts per million. For every million parts of atmosphere, there are 355 parts of carbon dioxide. And in 2000, it was up to 370 parts per million, or ppm. Now, when you have to calculate percent change, this is a basic math formula. You're going to have this memorized because you're going to be doing percent changes a lot. It's always final minus initial divided by the initial. Okay? So typically, if it's going up, it's going to be a positive number. So take the final minus the initial. And if it's actually going down, it's going to be a negative number. So you could plug in some other numbers for that. If something is going down, it's going to be a negative change. But this one is increasing, so it's going to be positive. So we'll plug in the numbers. 370 minus 355 divided by 355 times 100. So you're going to multiply or do this subtraction first, and you'll get 15. So when you take 15 divided by 355, you get 0.042 blah 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 times 100. Remember, it's percent change, percent multiplied by 100. The cent means 100. Okay, so when you multiply by 100, you get 4.2%. That is how much has increased between 1990 and 2000. And you'll see it's gone up ever since. So there might be other calculations that you could also perform. Okay, so for FRQ practice, I would like you to explain how fossil fuel combustion has altered the carbon cycle over the past 250 years. Write your response, and we will be discussing this in class. Thank you very much for your attention, and I will see you soon.